Okay, we've come to the last topic in geometric optics that we're going to worry about here, and that's lenses. So let's talk a little bit about what ray diagrams look like when we're dealing with lenses. We've got two basic categories, and that's converging lenses, which will have a positive focal length, and diverging lenses, which will have a negative focal length. So this is just like concave mirrors and convex mirrors had positive and negative focal lengths, except there was kind of an easy physical reason for thinking about it. When we think about these lenses, we're going to treat them mostly as thin lenses, which means they're just going to exist really only down the center of their axis. So we will again have, our principal axis that we draw through. Hopefully, you actually use a straight edge so that you get a straight principal axis. That's a nice line there instead of just sort of winging it like I did there. Unlike mirrors, we will have a focal point on each side of our lens, so it's kind of different. Oh, please, by the way, forgive me if I accidentally say mirror instead of lens or lens instead of mirror. It gets tricky. So diverging and converging lenses treat light a little differently. So if we look at a converging lens, if I send rays of light in parallel to the principal axis, then what happens is that they all will pass through the focal point. They'll converge at the focal point, if you will. Whereas, let me put all these arrows in. If I send rays of light in parallel, whoa, I don't know why they're drawn up there. If I send rays of light going in parallel to a diverging lens, what will happen is that they will appear to come from the near focal point. Which is kind of a weird thing to think about, but so it goes. So it can get a little tricky to sort out which focal point happens which time, but the useful thing to know is that for a converging lens, the rays are bent towards the axis. For a diverging lens, the rays are bent away from the axis. So, let's take a look at an example. Let us consider for a moment a nice little converging lens. Let's scoot this down a bit. Nice converging lens. So the line down the middle is where the lens basically is. That's where we're going to do all of our measurements from. We'll get a principal axis in here, which looks something like this. And we'll put some focal points. Let's say 1, 2, 3, 4, 5 boxes away. 1, 2, 3, 4, 5 boxes away. On either side, because lenses, there's not a real side and a virtual side, as obviously as there was with mirrors. Let's put an object hanging out here, about 2 boxes away. And now we're going to draw our 2 rays to locate this object. First ray goes in parallel, out through F, just like when we were doing with spherical mirrors. Second ray goes in from F. It's F on the other side of the mirror, basically, that we're worried about, either from F or through F. Do something like this, and then out parallel. That might look a little tricky, but it's important to think that it's still being bent towards the axis. So, looking at these 2 rays, we see they do not intersect. Since they do not intersect, we go back to our tried and true method when we have the situation, and we extend virtual rays backwards. We used to do this into the mirror, but now we're kind of doing it into the lens. So back here is where our image will be. So, object, image. And we can check this. So we said that F was 5 boxes. We said that DO was 2 boxes. And it looks like DI should be 4 boxes, right? 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 3, 4, 5. Right. So, same equation that we use for mirrors is still going to hold for lenses. Now it's going to be called the thin lens equation. Only holds for thin lenses. That's kind of the trick of it here. So we have a fifth equals a half plus 1 over di, which we want to find. So A fifth minus a half equals 1 over di. Looks like 10 is probably going to be our common denominator, so 2 over 10 minus 5 over 10 equals 1 over di, which looks like negative 3/10 equals 1 over di. And then the important part, this is the tricky bit. I have to flip this, because I don't want 1 over di, I want di. So di looks like negative 10/3, or di equals minus 3.33 repeating. So if I go back and look at this, that's not too bad. And again, these things are always going to be subject to how straight you've drawn this and how well you've made your lines actually go the directions they're supposed to be. So a little bit off. It's in the same neck of the woods. The important things, it's negative because this is virtual. Right. If I were to check the magnification, I would see that the magnification should be minus di over do, which should be minus 3.33 over 2. And an extra minus for good measure. So magnification is positive. And it is also bigger than 1. So this means that it is upright. This means that it is magnified. Both of these I see to be true looking at my image. So this is one way you can get a virtual image from a lens. Let's look at the other way, because these tend to be the harder cases. The other way is going to be from a diverging lens. Whoa, that is not even close to a straight line. This is why we have pieces of paper near our desk to use as rulers, because the rulers that are metal don't quite interact nicely with the touch screen, and weird things happen, and then you don't get lines at all, and yeah, stuff happens. Alright. Something like this. We'll draw our axis down there just to make sure we know where we're aiming for. Let's see here. That's a little too zoomed in. Middle of this looks like. So the downside, you have to make sure the pen goes first, then the hand, or else it thinks you're trying to put in crazy touch commands. Probably could have made this a little easier for me to measure things. 1, 2, 3, 4, 5, somewhere around here. 1, 2, 3, 4, 5, somewhere around here, I guess. We'll actually put them on the axis. Let's put our object, I don't know, maybe here-ish. And so again, we are going to draw our rays. First one is going to go in parallel. And since this has to diverge, it's going to go out from F. So it goes out something like this. Again, same kind of rule, but plays out a little differently. Since this one went from the near focal point, the next one's going to aim for the far focal point. So I'm going to connect up those 2 points, draw a line in to the mirror. This goes into F and then out parallel. And not as parallel as it could have been. Parallel, sure. Alright. Again, these rays, as we suspected, do not intersect. So this means I'm going to get, I know, a virtual image. And I know this because I need to extend these rays back into the lens. Whenever we do this kind of thing, we're always going to get a virtual image. It's always going to be an image that looks like it came from somewhere, as opposed to looking like it is somewhere. No projecting this. It's an illusion kind of in that it appears to come from here. So down here is where our image seems to be. That's not how you spell the word image. Let's try putting a vowel in. There we go. Image, object. And we can check again. This is about, let's see, 1, 2, 3, 4, 5. So F looks like it's about -5 because it's a diverging lens. 1, 2, 3, 4, 5, 6, 7.5 for DO. And the image looks like it's about 1, 2, 3-ish. Oh, and I should also point out here, this really should have been -4. Sorry. Because again, virtual images have still negative lengths. So, still using the same old equation. Again, you get a lot of mileage out of this. So we have negative 1 over 5 minus 1 over 7.5 equals 1 over DO. That's a DI, not a DO. Alright, so quick note, 7.5 is 15 halves. So this looks like minus 1 over 5 minus 2/15, because then 1 over 7.5 would be the flip of that. Nice little trick. Why do I do that? Because now it's a lot easier to add these things up. That's 3/15, 2/15, which is usually known as minus 5 over 15. Wow. I did a nice job with my picture this time. Again, we flipped because I want to know what DI is, not 1 over DI. Check out that. Boom. So, again, we could go check the magnification too if we want. We see it's definitely reduced, which we should expect. DI is less than DO. It's upright. DI is negative. That makes sense. The magnification will then be positive. Yeah. So hopefully this helps you figure out some of the basics of ray diagrams. You should take a peek in the book if you need a little bit more. And yeah, good luck.